Hey everyone, we're just about to get started. We're just waiting for our co-host to join us. He should be getting in any second, but welcome to the stream. I'm very excited about this one. Um, Let me just double check where we are on stuff. But I've been looking forward to this for a long time. I've been big 1553 stuff for most of my career at this point, so it'll be a fun discussion topic to talk about. And I see Andrew giving us a welcome, but Andrew, you were supposed to be in the. Oh, there he is. There we go. Let me add you to the stage. How's it going, Andrew?
Good afternoon. Can you hear me?
Yep, we can hear you.
Awesome.
So I will go our team. I figured we would just have him on to provide some commentary, and he can help me manage questions and stuff as they come up for you guys. So let me go ahead and share my screen, and without much to do, we will get started. Okay. And cool. Oh, except we need to start on the first slide. Okay, so welcome to our aviation security workshop. We're really excited to have everyone here. Like I said, I've been looking forward to doing this for a long time, but we'll get going. Unfortunately, Kevin couldn't join us this time. But if you haven't heard anything from me before, we have a BS in astronautical. I have a BS in astronautical engineering, so I started off as doing rocket motor modifications for the Air Force. Then I got put into a test squadron doing missile testing for fighter jets, and at that time they decided that everyone was going to start doing um, cybersecurity testing for aircraft. This was part of NDAA 1647, and I walked into work one day and they decided I was the new cybersecurity expert for running cyber tests against aircraft, and that's kind of where I got started um, with all of this 1553 stuff. I got and just aviation stuff in general for in terms of cybersecurity. That was back in 2016, so 9 years ago now. Um, and then after that, I went to a information aggressor squadron in the Air Force, where I continued helping to run cyber testing against aircraft, as well as doing some more traditional offensive red team stuff as part of like the Air Force's red flags and cyber events and stuff. After that, I went to Boeing FanWorks. If you've heard of Skunks Works in Lockheed, FanWorks is Boeing's equivalent, and I was one of their lead engineers for doing clean sheet design on aircraft while I was there, specifically focused on security. And so I have, like I said, I've been in doing aviation security stuff for about 9 years now. When I first started off, there were only a handful of us that were doing it, and most of them were like me, that had just kind of gotten into it, and there wasn't a lot going on. That's drastically different now. um, Everyone is looking at it. You know, when I started at Boeing, there were like 10 of us in the whole company. By the time I had left a year and a half ago, they had hired like a couple hundred and were training people and had created an entire job code based around it. And so things have grown rapidly. But just before we go into the aviation stuff, you want to give a little background on yourself, Andrew, just so everyone
Yeah,
knows who
absolutely.
you are?
My name's Andrew. I'm relatively new to the cybersecurity world. I'm an Army vet, and I went to college for computer science. I did about 5 years at Home Depot as an analyst, and then I got out of that. And ironically enough, I went into the film industry where I worked on movies and TV shows for the last about 8 years. And with how slow things were moving in the movie world, I got an opportunity to work with Coin and Hubble, and I've been learning cybersecurity ever since. It's awesome. I can't learn enough, and I'm
Yeah.
just really excited to be here.
Yeah. So that he's going to be our co-host, and we'll go ahead and get started. So aviation security covers like a really broad area of stuff. It's the protection of the air vehicle and its systems. I'm starting it. We're going to start with the really broad picture, and then we'll kind of focus down onto the 1553 stuff in a little bit, just to give context for like what security is. You have it, when you're talking this as a holistic thing, you have everything from like the ground support systems. So that's like your maintenance laptops, your like all of the luggage stuff that gets put into the aircraft, fuel pumps, all those kinds of things. Generally, we'll be focusing mostly on those maintenance laptops because if we're trying to get into an aircraft, that's kind of where you'll be focused. But will for the most part, but it covers everything. It includes the air, and then you have the airport, which has all of the, um, staffing stuff to make sure people get to their flights and all those kinds of things, which is where we have seen like real world hacks. Like we've seen airports. I have a slide pointing out the CrowdStrike thing last year that took down a bunch of airlines for their stuff. Um, and so that's where we have seen like real world attacks, as well as in that external communications part. That's the external communications is going to cover everything from like ADSB, which if you go to DEF CON, like you can go take a workshop on hacking ADSB at DEF CON now, to GPS spoofing on the military, to like more things on the military side, which are like your radio frequency um, communications, like a little different than ADSB, but because they do like ground troop support and some other various types of radio stuff like Link 16 and those kinds of things in the military. But those are all their kind of own segment, and you can divide those up into satellites and RF, and we'll get to that in a second. Um, so aviation, especially when you're talking about the aircraft portion of this, is a lot different than traditional cyber security because it has this safety thing that can never be overridden. There is always going to be safety trumps anything. Like when you're designing security, when you're designing aircraft stuff, and as part of that is reliability. So, like one of the things that we dealt with a lot was like how do you do software validation on certain aircraft components? Because like if you have the flight computer that's like the brains of the aircraft, and that goes down, and like you try to, and you need to be able to do like an in-air reboot. You can't risk like a hash failure because you would rather have the aircraft on with a bad operating system than like the flight computer not on at all. And so that creates some interesting friction points for when we're trying to design security and stuff. It's also why when we get into 1553, a ton of these issues exist because everything is designed around reliability. Um, you also start not just that reliability safety stuff like that in-air reboot, but you also have like start and restart time performances. Like part of that restart time performance is a part of that reliability for or that time constraint for like civilian aircraft. On the military side, you sometimes have things like the aircraft needs to be able to start up within X minutes or whatever, so that like if China surprise attacks us, then then we can go ahead and get those aircraft off the ground. Less of that kind of takeoff time is less relevant on the civilian world. And then you have this size, weight, power, and cost restraint. You'll see swap C a lot at aviation stuff. So not only do we have like the restrictions of reliability, we also have the restrictions of like how much power a computing system can take up, as well as like very limited memory spaces. So some of the challenges we've had to work on in the past were like if we are going to do like a hash or a signing of code how can we manage that when like the memory registrar is not large enough to hold a traditional like hash or private key signature? Like it's not big enough, just because of the size of the components in the system. So all kinds of things like that. And then something that was just kind of a hindrance to aircraft security for a long time in terms of getting people to take care of it is the fact that aircraft are quote unquote air gapped. So a lot of people didn't think they were really all that hackable because there wasn't any a direct line from like the internet to um, okay, 1 second, guys. um, I Anthony is telling me he needs to check some. I need to check something. 1 second, please. I'm just gonna stop sharing my screen for a second. I apologize, guys, but Anthony is saying it's urgent. Um, okay. Looks like a Zoom meeting somehow went out that was not supposed to go out. So 1 second, guys, let me just get the Zoom people over here. I apologize for that. 1 second. Just give me 30 seconds. Okay. Andrew, can you talk to Anthony? Because like when I look in our Zoom meeting, there are no meetings scheduled for us. So I'm not sure what meeting people are in. It's not under our Zoom stuff. You there, Andrew? Oh,
There
hold
you
on.
go.
Andrew got dropped. Okay, sorry.
Yeah, I'm talking to Coin right now.
Okay, thank you. We'll keep going then. Yeah, I'm not sure. Like, I'm in our Zoom and I don't see anyone, or see a meeting there, so I'm not sure what meeting people are in. Okay, we'll go back to sharing. Sorry about that, everyone. We just want to make sure everyone can get in. I'm failing at sharing my screen. Okay, so with all of that said, how often do aircraft actually get hacked? There's like in the early to mid like 2010s, or I guess mid 2010s to late 2010s, there were like a number of stories that came out about like people claiming they had hacked stuff. Like a big one was at Black Hat a couple of years ago, where a researcher said that like they claimed that they had gotten access to 787 source code and had determined that there were major vulnerabilities in the software. Um, well, like, so I was at Boeing at the time. I'm not going to defend Boeing as in saying that they have done the best job in interacting with the security community, because they definitely have been standoffish and difficult to work with in the past. Um, but I do know that like they went and tested, like I know the people that went and tested the code, and like that guy claimed that he knew for a fact that there were security issues that would allow for like remote takeover of the aircraft. Um, without ever being able to compile the code. So all he did was like a static code analysis, and he never even ran any of the code or tested anything. He just was adamant that those vulnerabilities existed in the code because his static code analysis tool told him that it was there. And when it was went and tested, no one was able to validate any of his findings, and he didn't like those. Same with like back in 2015, I'm blanking on the guy's name, but he claimed to have taken control of an aircraft, and he was supposed to give a talk at DEF CON, and like right before it, the FBI like arrested him or detained him. I'm not sure if he actually got arrested or if they just prevented him from giving the talk. That one is unclear on whether or not he actually was able to. That of all of the claims that people have made of being able to hack an aircraft, that one is the most legitimate because most of those things stay closed. That and the one up that I have up here that says Boeing 757 testing shows airplanes vulnerable to hacking. That was actually done by the Department of Homeland Security back in like 2017, and they hacked a 757 sitting on the tarmac. They never published how they did that, but they did say that they were able to do it, and the details of that were classified, which so we never got to see them. And then like the most recent one was a couple of years ago at DEF CON. They had a HackerOne competition partnered with the Air Force where they let hackers go quote unquote hack an F-15. Um, that wasn't really hacking an F-15. It was ground support equipment for the F-15. And they did find vulnerabilities like that would have been an issue, but like they didn't hack a F-15 like remotely in the air or anything like that. They got access to hardware, reverse engineered it, and were able to find issues in the ground support equipment, which is a significant issue. That's not to take away from the idea that like what they found wasn't problematic. It was just that there was a lot of it was kind of blown up into a bigger deal than what it was. Um, yeah, Chris Roberts, thank you. Yeah, it was Chris Roberts. So that's kind of the like people have claimed to have hacked aircraft, and it's debatable on what's real and what's not because it's always big headlines. That being said, if you're talking about radio systems and communication systems of aircraft, those have been hacked pretty significantly. The two biggest ones being ADS-B and GPS. GPS spoofing is trivial nowadays. Like pretty much anyone can do it. Lots of airlines are reporting like huge surges in the amount of GPS spoofing they're encountering. Um, for like ADS-B, the Aerospace Village badge a couple of years ago was like a whole ADS-B receiver that you could spoof yourself. Like I said, you can go find projects on GitHub on how to mess with ADS-B. ADS-B is an air awareness system. I have it in a few slides, but it just tells you where other airplanes are in the sky. It's totally unauthenticated, so someone can send a message saying like, "Hey, I'm an aircraft and I'm here," and the system just believes them. So it's very trivial. And then there has been some reporting that ACARS has been an issue, which is a aircraft communications addressing and reporting system. It's a way for aircraft to be able to send messages between each other. The EU said that they found some issues with it. Details on that were scarce, but that's out there as well. Um, Yeah, so we're not really sure. Just for the people joining us from Zoom, I apologize. We're not really sure what happened with the Zoom link because there's no Zoom meetings in our account. So I apologize. We're not really sure what happened on that. It seems to have been some automation through Eventbrite that like added the link, but then it didn't get added into our Zoom account. So I apologize. Yeah. So we've kind of talked about all this. Now you get into the different segments. We talked about all those things, but you can break aircraft into different segments for information boundaries for analyzing them. Um, you have kind of the space segment, which is all of your satellites. And this is space satellite comms are used very heavily by modern aircraft for various things. On the commercial side, it's primarily GPS and Iridium for actual operational needs of the aircraft, and then Starlink for like and other commercial internet solutions for the onboard Wi-Fi. So like when you have Wi-Fi flying over, the Atlantic Ocean or the Pacific Ocean. Um, they also use it for tactical C2 in the military. Um, those are the biggest ones that we can really talk about here. GPS, like I said, super easy to hack at this or to spoof at this point, or to jam. Uh, Iridium is considered critical infrastructure used for air traffic control. There has been published eavesdropping attacks on Iridium in terms of using Iridium as an entry point into a network. I didn't find anything when I looked for it, at least open source. And so, but there has been stuff published that there have been vulnerabilities found in the Iridium satellite system. Same with Starlink. Starlink's had a number of issues published about problems with security on it. It's much better than it used to be, but there have been a number of people that have posted how you can compromise Starlink connections. Radio frequency is kind of where you'll see the most speculation on actually hacking an aircraft remotely. DHS, that one that I said they didn't publish a lot of the details on it, they did confirm that they were able to gain access to the aircraft through radio frequency transmissions, and that was kind of the only details they gave us. But there's a bunch of radio frequency stuff used by aircraft. I kind of put some of the big ones up here, which I mentioned the ADSB, which is for air awareness, know where other aircraft are. There's the TCAS system for collision avoidance. Then there's a line of sight radios, which are primarily for government use, but some aircraft, depending on what part of the world you're in, do have line of sight radios used for ground communications with the air traffic control as well. They can be encrypted or unencrypted. And then there's other ones like not ITOLs, but something like that. Like it's an infrared one used for landing it, helping aircraft find the runway when they're landing. There's a bunch of them. This gets us into ground support systems. On the civilian world, they're sometimes referred to simply as maintenance systems. If you call it ground support, sometimes they think of ground support as just like the stuff used for like transporting the air or the luggage from the aircraft to the terminal and those kinds of things. This is the area where we actually see attacks. CrowdStrike was an attack, but it took down a huge chunk of the air industry when it happened, because without the ability to do flight planning and crew management, the aircraft can't take off by themselves. So there's problems there. Obviously, like in an emergency situation, sorry guys, they're still trying to figure stuff out on the Zoom link. Give me 1 second. No, Andrew, I'm signed in under my info at BC security account.
I think Dorf's working on it.
Okay. Can you just let him know that no, I'm not signed in under Jake Kress. I'm signed under the BC security one. Yeah. So the flight planning and maintenance and diagnostics includes a lot of different things for the ground support equipment stuff. One of the ones that I like to highlight on here is like load and balance, because something that is interesting in the aviation industry from like a relic is that a lot of times stuff was protected based on like IP stuff for manufacturers, and they would protect certain critical components like the actual like flight computer software, but they wouldn't necessarily protect things like the load and balance data, because that's entered at the time of like flight, like after the flight master has loaded all of the cargo onto the airplane, they then enter load and balance. But like if you told a plane that it was taking off with 100 pounds on the left wing, or probably more than 100 pounds, 1,000 pounds on the left wing, and there really wasn't anything there, the airplane would probably crash because of the way the flight controls would try to compensate for the weight, for the imbalance on one side, or vice versa. If it thought everything was balanced and it's not balanced, you can cause major issues in an aircraft there. So ground support systems often create bridges between internet connected systems in the aircraft. So even though we call them air gapped, typically you'll have like a maintenance laptop that'll be plugged into the internet to get software updates or map updates for the navigation systems or all those kinds of things. That laptop then gets carried over to the aircraft and plugged into the aircraft to load things in. So it is technically air gapped in the sense that it does not have a traditional internet connection itself, although that's also changed a little bit with like Starlink and that kind of stuff for commercial aircraft. But in the traditional sense, it is technically air gapped, but jumping an air gap with a laptop is not very hard. Like we already have seen, 25 years of the ability to jump air gaps using like USB and CDs and stuff, which is a significantly harder challenge than if someone's just taking a laptop and plugging it into the aircraft. So they are technically air gapped, but not really is kind of the thing to go. So there's lots of attack paths to get into that. We're going to move into actually talking about the aircraft itself, but I'm going to take one second here, guys, to check to see if we can solve this Zoom issue real quick. Let me check something. I'm just going to try one thing. Okay, this looks like we may have found the issue.
Just so you know, Jake Dorf is sending out an email to everybody that signed up and sending them like the Twitch link and YouTube link and LinkedIn and everything.
Okay, let me see. I think I might have found the issue. Oh, there is one. How did this? I haven't logged into this account in like forever. So okay, 1 second, everyone. We'll see if there's people in here still. It doesn't look like there's anyone still on this, so let me just drop the link in here. Oh, there's a few people joining. Okay. Hold on 1 second. Sorry, everyone.
I see Pyro Freaks telling me about B-Sides Las Vegas.
Okay.
Didn't B-Side have a Tampa last week, Pyro?
Oh, why is it? Okay, so we'll get into aircraft now. Sorry about that, everyone. So we're going to be focusing on the internals of the aircraft from here on out. Some basic terminology to go over is you'll hear the term line replaceable unit a ton in aircraft. These are modular electronic components that can be quickly replaced. So like the radios that we were just talking about are generally in a self-contained unit that literally slides out of the aircraft, and you can take a different one and just slide it back in and plug it in. One of the things that is interesting about those is that for the most part, there is no authentication for line replaceable units. So when you are on the flight line and someone swaps out a radio, if that radio has been compromised in some manner, or is someone just plugs in a line replaceable unit in somewhere on the bus because there's an empty spot, which happens because aircraft are built with like extra connections for like the expansion of capabilities later on. Generally, there is no way uh, on most systems to be able to detect that a rogue device has been connected, and we'll talk about how that's bad later on. Built-in tests are built-in methods for self-diagnostics. So generally, every LRU will have a bit test that can be ran to check for functionality, and those bit tests are something that lead to non-compliance with 1553 protocol that we'll talk about a little more. And then just as a joke, flight computer. So you heard me call that. A lot of people refer to the main computer as the flight computer. Sometimes you'll hear them call a mission computer and stuff. If you talk to like a hobbyist pilot, a flight computer is a slide rule that looks like this thing over on the left or on the right. So if someone gives you a weird look, if you mention talking about hacking a flight computer, it's because they think you're talking about a slide rule. So just funny. So the protocols are there's kind of four primary protocols. It's really three, but there's still a number of aircraft that are in service that are using the fourth one. So I went ahead and said four. ARINC 429 is probably one you've heard of. If you've ever gone to DEF CON and gone to Aviation Village and they had like a CTF or hack, it's ARINC 429. That is a point-to-point one that we'll talk about in a second. It's the most basic of all of these. It's and kind of the least interesting to mess around with, other than it's like on an aircraft. Then you have ARINC 629. This was a bridge protocol that solved the point-to-point type of thing. And there were like 3 aircraft that were built with it. One was a Boeing, and then there were 2 Airbus aircraft that were in terms of like major manufacturers that were built with it. Airbus still produces one of them, I believe, but the rest might either 420 to most likely 664. A handful of civilian aircraft do use MIL standard 1553 in certain components. Like I think Embraer has used 1553 in their civilian manufacturer. So ARINC 429 is super simple. It only supports point-to-point connections. So if you have 3 devices on an aircraft and you want each of them to be able to talk to each other, every device needs 4 wires. It needs 2 wires going to the other 2 components, and it needs 2 wires coming back. So each wire, it can only be used either for send or receive, and you can only go point to point. So from a engineering standpoint, it's very heavy to build an aircraft with this because of the amount of cabling required to network a bunch of components together. Technically, it also makes it a little more secure than the other protocols that we're going to talk about, because you can only talk to like directly to other devices. You can only talk on one line at a time. So like trying to DOS the entire network like doesn't really work in 429. So it's interesting. It uses 32-bit words, which we'll talk about a little when we get into the deep dive of 1553, but these are different structures. So like none of these protocols really have commonality across structures or anything, other than they use kind of the same size words. So 629 moved into a more traditional, or not more traditional, a more functional bus network where you had 2 trunks. If you look at this will look very much like 1553. It is probably heavily influenced by 1553 because it came out after the 1553 protocol had been designed. And it was a transitive solution between 429 and ARINC 664. Still peer-to-peer data transfer. So one of the things that is interesting about this versus 1553 is that 1553 has something called a bus controller that is responsible for orchestrating all traffic on the network. Without the bus controller, the protocol doesn't work. ARINC 629 works on a peer-to-peer transmit implementation. The problem with that is that it means that the protocol is not super flexible for dynamic allocation of tasking to your controllers, because everything has a set timing that it's allowed to use. 1553 also has set timing, but it can be updated by the bus controller to allow for like a device to talk out of standard turn and those kinds of things. Whereas 629, you can't really do that because no one else on the bus will know that you're trying to talk when they're trying to talk. So you'd have to have a way to command all the terminals on the bus to stop talking all at once, and it just doesn't work very well. But like I said, it was a bridge network. It was used on like 3 aircraft, and then in terms of like large manufacturing builds, and then that was kind of it. So ARINC 664 is our modern bus architecture. This is what is used on commercial aircraft that are being built now. The main thing it did was that it moved from like oh man, what's the term I'm looking for? It was twisted pair copper cabling to traditional Ethernet cabling. And it does use like Ethernet, like TCP/IP frames. They are different, but it uses that concept. So it allows for devices that can speak Ethernet, like on Ethernet cables, to be able to use off the shelf instead of have to create custom connectors and implementations for devices. So it made development time for aircraft much shorter in terms of integrating new components. So this is why you can get like in-flight entertainment stuff like much easier now, is because they moved to ARINC 664, which made like sending video and all that kind of stuff much more feasible, much higher throughput as well for data. It still has deterministic timing, and then it has what it calls virtual links, which are one-way data flows. So within the routing of the network, everything is a one-way data tunnel. So it's kind of sort of like a ARINC 429-ish implementation where there's one link between each thing, but it has complex switching that allows for those links to be a little more dynamic. So you can send out broadcast messages and stuff that makes it more useful. The whole system as a whole overall is just way better than all the ones prior to it. Although you still don't necessarily see military aircraft moving to ARINC 664. They still use 1553, like the F-16, the F-22, all those still use 1553. The F-22 there was talks of changing it over to a different protocol. I always forget the exact numbering on it. I think 1776 is basically 1553 over Ethernet, is what they had talked about moving to. But as of yet, there is not a fielded U.S. or Western military aircraft that has moved off of 1553 that I'm aware of. I say Western because China and Russia do have their own bus protocols. I think China may have started adopting MIL standard 1553. But yeah, Russia has their own that they've been using for a while. They may have also eventually moved off of it. I didn't go check before we started this. So now let's get into the actual kind of hacking of what we're here for. That was kind of an overview of all the stuff that goes on in aviation, since not a lot of people have gotten that context. MIL standard is super old. MIL standard 1553 is super old. It was originally published in 1973. There was a MIL standard Rev 2 or 1553B published in 1979. I have the number on here. And then there have been a few minor updates to it since then in the 80s, but since then it really hasn't been touched. So as you can imagine, security was not built into this protocol because it was just not something anyone thought about at the time. If you see down here, these are our bus controllers and remote terminal and our bus monitor. It looks very similar to that ARINC 629. You have redundant buses so that basically if one of the buses becomes unreachable, there's a failover bus. Some systems will have a third failover or have a third bus that is also a failover. They'll have two redundant failovers, but that's pretty uncommon, just because it starts getting heavy and you run into that size, weight, and performance restrictions that we were talking about before. It's been adopted into satellites. That's the biggest area you'll see 1553 in the civilian world. So there is relevance to this stuff if you're not just if any military or government type of work. It is heavily used in satellites. Some commercial air, like I said, and then I found out yesterday when I was just reviewing stuff that apparently there are some trains that use 1553 for safety critical functions just because of the reliability of the protocol. So maybe you'll get a chance to hack in a train with mil standard stuff. So this brings us to the demo. I apologize. I am not very good at Docker, and I tried to get stuff set up with a Docker Compose file that would automatically pull everything for everyone, and it did not work. So what I have published the Docker files at on a Docker repo that they can be pulled from. And hold on, I'll give you guys the link to the sim with the YAML for running it. So I'll show that. So it's on our BC Security GitHub. It'll like it's yeah. So what you'll need to do is is you'll download them from this repository I built. With Docker, and then you can run the Docker Compose and it'll execute it for you. And then the web host will be available. Like I said, I apologize for that. I thought I had like a YAML that you just be able to do like Docker Compose up with and it would pull everything. But when I was testing it this morning, I just couldn't get it working. I will do better in the future for you guys. But once you do have it up and running, you can just run the Docker Compose. You just run the Docker Compose up, and it'll start. And then you get a nifty little interface like this. So it'll show you when the bus is busy, when it's getting signals from various LRUs on the aircraft, along with some information. Like you'll notice if you watch for a little bit, like this will actually move, like the aircraft is flying, and then the radar will also like show a target that is moving around a little bit. And then if you click on these arm weapons, you can go ahead and like arm something. So you'll see the weapons now armed. And then the most important one, which I'll zoom in here, thing to remember is you have two different boxes up here. There is your source and destination, which is this top one for sending commands is to allow you to send legitimate commands on the bus. So this is like if you want to just like play around with sending commands, but like from the BC or from the bus controller to like an RT, like legitimately. And then this one down here is for spoofing messages. If you try to just send like a random message, you'll notice that it says this bus busy thing down here. If you try to send it while the bus is busy, you'll get a note. You can pause it. You'll get a collision notice because if you try to send stuff while there's outside of your timing window on the bus, it'll break. The only exception to that is to the BC, so that we can pretend like we're directly controlling the BC. If you send stop to the BC, it'll stop sending. We'll get into how the structure works, but you'll see that the BC is sending commands to all of the RT remote terminals, and they respond with the information just like they would on a 1553 bus. One thing to note: this is a simulator; it is not an emulator. So while we built this to try and replicate the feeling and effects of 1553, it is not actually doing like 1553 protocol stuff on the back end. It's really hard to get. The reason for that is 1553 has super tight timing restrictions, and building a system on a computer without a ton of dev work and writing like hardware level emulation stuff, it just doesn't really work because none of the TCP/IP protocols enforce tight enough timing. So this is a simulator. It is not truly like an emulator. There are like things that aren't quite exactly how it would work in real life, but it does like allow for a lot of things. You can decide where. We'll talk about what this address means in a second, but like you can send an RT1, and if we try to send it a command that doesn't know, you'll get like a response that back like it says it doesn't know what's going on, which is normal. That is actual behavior. If the RT doesn't know what to do, it responds with an error message to the bus controller, and that's like a good transition for us to start talking about the protocol a little more. So let me see. Does anyone have any questions so far? Let me just check the Zoom chat and see if we had anyone over there. Oh. Okay. Let's see if I can do this. I didn't see people saying that they couldn't get it in. Let's see if it'll let me. Can you still hear me, Andrew?
Yeah, I can hear me. Can you hear me?
Okay. Yeah, so it looks like we're in Zoom. Let me see if I can also share the screen here, if I can do a double share. Okay, it looks like it is working. So we'll just run it on both now. Apologize, guys. It was supposed to be scheduled on like all of our social media stuff, like LinkedIn and Zoom and stuff, or in Twitch and stuff. We didn't intentionally send it out here, so I apologize.
We got a question, Jake.
Yeah.
It's in Twitch chat. Looks cool. Will the source code be available so others can contribute?
At the moment, we are not planning on publishing it, like just as in the next few months. We're not planning on publishing it because we're still trying to figure out some bugs and stuff, and it's definitely not quite ready for full publishing. We'll see about what that looks like in the after that, kind of like post Black Hat and stuff. We just have a lot of time. We wanted to run this workshop because a lot of people have been asking for it, but we didn't feel quite comfortable yet publishing the full source code on the tool. That's kind of out of character for us. We generally try to publish as much as we can open source. We just didn't think that this was quite ready to be fully released yet. So we'll revisit that again in another month or two once we had a little more time to dev on it. But we will leave the project up for people to use, like through the Docker containers and stuff. So if you want to restart the container or the bus controller, you just hit start, and then you'll start getting all your updates again. So it works like that so far, and then we'll jump back into things. Oh, I need to switch this. So my favorite resource for this, I will just grab it real quick, is this mil standard 1553 tutorial from AIM GmbH. They're a German company. They published this like, November 2010. So it's very old, but it works it's really good. It's the best one I found because it's very detailed, and this is where like a lot of the pictures in the presentation came from. Like you'll see these again in a second. For more reliability. But if you scroll down, my favorite part about this is like the reason I always suggest this is that it has like the actual protocol if you want to read the protocol like standard documentation, and then it has like a plain English version of like what does this mean, so that it's like a lot more understandable, because like a lot of this stuff is like very like technically dense, especially when you get into the where is it like the ICD stuff of like just the specific bits and stuff. Like it's just very dense, so it has some explanations and stuff on it. I will drop the link for everyone. So there's that, and then I will. Which screen am I sharing? Oh, whoops, I'm sharing the wrong screen on this one. Oh, it's sharing the wrong thing. Okay, well, we can do it this way. I'll post a comment here. We can full screen like this. Okay. So Mil Standard 1553. Oh, let me switch out. Can you change which message we're showing, Andrew, so that it shows the link for the Mil Standard document?
The one that you just posted?
Yeah, if you click on it, it should let you like highlight it to make it. Here we go. I got it. There we go.
Oh, I got you. I'm sorry, I missed that.
Yeah. So yeah, I really like that one a lot. Go ahead and do this again. I've been using that to teach engineers for a while now, so it's very useful. So it's Manchester encoded, which just has to do with the way the voltage works. 90% of the time, unless you're doing like hardware hacking stuff, that part's not really going to matter to you as much. Multi-branch support is important because you're only allowed to have 31 remote terminals on a single 1553 bus, but it is illegal in the bus protocol to create branches. So you can have a second bus hanging off a first bus and then have more remote terminals on it, which is how like modern aircraft are built, because most of them do have more than 31 terminals. It's transmitted as most significant bit first. That's just important to know for decoding the data when you get it. Has really robust error handling. That is one of the biggest things it does have. It has robust error handling and high reliability. Those are the two things that are most important to it. Data packets are referred to as words, and that's just kind of like if you think like a TCP/IP frame or a TCP/IP packet, or frames and packets are not the same thing. The TCP/IP packet is kind of similar to what a data word is. You have the three key components within 1553, which are the bus controller, the remote terminal, and the bus monitor. The bus controller is the big boss. It's what controls everything, and by standard is the only thing that is allowed to communicate on the bus without first being told to talk. So the 1553 protocol functions off of a don't speak unless spoken to concept for all of the remote terminals. And the bus controller is the one that gets to be the one that speaks to everything. Remote terminals are just any device that's that's coupled to the bus. So in modern aircraft, not everything is 1553, so you'll see stuff that's hung off the bus using like Ethernet, but it has like a coupling to it. It's also like how all your radios connect and all that kind of stuff. And then finally, you have a bus monitor, which is by standard again. And when I say by standard, that means by the mil standard 1553 standard. By standard, a bus monitor is only allowed to listen to data transmitted on the bus. If it is defined as a bus monitor, it is supposed to be a passive device only. But sometimes that is not the case. Your standard topology will look like this. You'll have a primary bus and a secondary bus with RTs and a bus controller and a bus monitor. That secondary bus is meant to be a failover, so we'll talk about DOSing the bus and how easy that is in 1553. But because everything is highly reliant on copper cabling, if you have something like a short in the aircraft, you can end up with the bus DOSed anyway. Like, and it's not an intentional thing. Like if you have a short in a remote terminal, there's like ways that the bus can become unavailable, and so it has a backbone failover that the remote terminals can talk on. It can also be used for like if a device is talking a bunch on one bus, the BC controller can send a command on the other one to turn it off. Like if it thinks that the remote terminal is misbehaving. But again, it is by standard that enforces that an RT or a bus controller can only talk on one of the buses at a time. So you're only supposed to be talking on A or B. You're not supposed to be talking on both at the same time, but there's nothing that actually enforces that. So a compromised RT could talk on both and compromise the bus. This is that multi-branch architecture that I was talking about. So you'll see where you have like your flight control computer and then like the cockpit display systems. Then you have like the main backbone, and then you have the vehicle bus, your navigation bus, and your comm bus, and then like your stores. Stores are the technical term for weapons on a military aircraft. So one thing to note here in aircraft architecture is you have what they call the vehicle bus here, and then you have the global bus. In this one, it's not the case where you have the FCC right here, this flight control computer on the global bus. A lot of times this flight control computer will be on the vehicle bus and the global bus, and they'll separate these flight critical functions with the flight control computer to allow for more isolation of those functions where like if the cockpit goes out, then the flight control computer can still potentially be controlling things. So that's just like one thing of note, that a lot of times they will try to isolate the flight critical functions from some of the other like mission critical functions. And that's like an important thing to keep in mind if you are probing a bus. So when you're talking about comms from stuff, it follows very strict timing requirements. Gaps between messages are supposed to be enforced at the microsecond level for timing. And then, as I mentioned, all communications on the bus are initiated by the BC. So how this will work is the bus controller will send a command to the RT. If the bus controller requested data from the RT, it respond, or if it requested for a status, the RT will respond to the bus controller with a status message, and then the bus controller decides what to do next and sends additional commands. The message structure. So this is where we're going to actually start talking about how we hack the bus, other than just a straight DOS. So you have the sync command. What's important is this is a voltage differentiator that is actually non-Manchester encoding, so that the devices can identify that it's supposed to be a signal of some kind and not just like a bit. So these are like 2 bits wide instead of 1 bit like you're supposed to be in Manchester encoding. When you have positive voltage going into negative voltage, that indicates that it's a command word. Command words are what a bus controller sends to a remote terminal to tell it what to do. After the command word, you'll then have a data word, and what's important is that the command word informs the remote terminal how many data words are supposed to be coming. You then have the data word come, and it is 16 bits big, and it has all the information that it needs for the various commands that it was given. Once that is done, if you see this T slash, here, let me change this to the pointer. So you have this T slash R that stands for transmit or receive. This is how the bus controller, so this first part is how the bus control, or not the bus controller, sorry, the remote terminal knows that it's addressed to it. So the first part of command word is the remote terminal address. Everything gets access to every message on the bus in 1553. So what happens is everything reads the first message when you get this command signal part. It reads this first part, and if it doesn't match its address, then it just drops it by standard. So if you have something nefarious, it could obviously keep reading stuff because it has access to it. But normal behavior is it's supposed to check this remote terminal address. If it is not the remote terminal's address, then it just ignores it. The next bit um, is to tell you whether it is expecting to transmit or receive data based on the command word. And then these next two parts are going to be dependent on the remote terminal. It has subaddress, which is like various functions that tells it what to do, and then how many data words or what the mode code is going to be. And at the very end, you have a parity bit to check for errors and stuff like that. Then you have 16 bits with a different initialization for the Manchester encoding. And then once that has all been received and the remote terminal does what it's supposed to do, it'll send a status word back. And so this is one of the interesting parts about 1553 is when a remote terminal responds after it has been commanded by a bus controller, it includes its own address. Because I said that the remote terminal checks for if its address is included. By including its own address, it guarantees that no other remote terminal will think that the status word that it is sending to the bus controller is a command for it, because it uses the same sync command or indicator as a command word. So very important. This remote terminal address part is a key part of how this protocol works and is very easy for us to use, which we'll talk about in a second. And then just information on what's going on about it, then we can go from there.
Did you see what Pyro said? He says it's sort of
No.
seems similar to CAN bus in cars.
Yes, it is similar to CAN bus. CAN bus and 1553 share similar architectures. So if there's two primary transmission structures. There's that controller to RT transfer that I talked about. Like it says that bit back here says to receive. It then will receive a command with the data words followed. So the RT has to process that stuff very quickly because there is no gap between receive command and the data words. So general, it's supposed to be no bigger than like 14 microseconds, if I remember correctly, between these gaps. And in some cases, it's as low as 4 microseconds. So the decision tree on this receive command is very quick. After that, where you have the longer gap between the data that to signal that like there's a new command, you send the status word from the RT, and then you have these gaps are different sizes based on what's waiting for. That's what these two stars and the pound sign mean. Then you have a transmit command. This is telling the RT to send data, so there is no follow-on information from the bus controller when it sends a transmit command. It sends a transmit command. You have the break here where you'd normally see a status word. Then you have the status word with the data words from the RT until you wait for the next command. So without, or well, here we'll go back. You guys probably saw it, but without anyone. Can anyone tell me some problems they see in this architecture and from a security standpoint? Like anything that they think we could abuse? Yeah, so there's no auth, which is a big part of it. But what about like how does an RT know that a bus controller sent it a command versus if the command came from somewhere else? So that's looking at this. That's if we go back to our.
Somebody said easily spoofable as well.
Yes, it's exactly. So there is no way for an RT to authenticate where a command came from. As long as this matches the RT's address, it will read the command and attempt to execute it, as long as it has this command sync on it. So there is no way for a remote terminal to authenticate or to validate the source of a command. And so that means that we can do lots of stuff to various remote terminals on here. So the tight timing constraints are also abusable because you only have like 4 microseconds to determine what's going on. Sometimes the programmers and stuff don't have as robust checks as they should in their software, because they're trying to go fast to make sure that the RT actually responds in time. So you can do that. It also means that it's very trivial to DOS the bus. Like basically sending a command like every second will just DOS the bus because you obliterate the messages by stomping on them. And you don't have to have valid data, like I said, because this is using like that Manchester encoding and it's all like current measured stuff. Like just raising the voltage output on an RT can break the bus. So you don't even necessarily have to do that. There's also some interesting things that you can do for like trying to identify like solutions for stuff. By measuring like the resistance on the bus, you can theoretically identify when a new device has been added, and do some things like that. And then another part of the protocol is that timing is deterministic. So everything is given a timing window that it's supposed to be in. So if we are eavesdropping on the bus and we see a command go out saying like, "Hey, nav system, what is my current position?" We have a pretty good idea, especially if we've collected some data to see what the timing patterns are on the bus. We have a pretty good idea of exactly when that terminal is going to respond because of the timing constraints, which means that it's
You there, Jake?
top of the bus. So it's that is difficult just because you do have to be really tight in your ability to inject on the timing piece. So it's difficult from both ends. Otherwise, you just end up with invalid data. But it is something that is possible, and is something that makes it easy for us to predict on when data is going to be interesting to us.
Jake, Pyro wants to know if you can push too much data in the frame.
Yes. So you're jumping ahead. So, kind of. Well, we can. Oh, okay. I don't know why that just did that to us. Okay. Sorry, people on Zoom. So what happens is if you try to push too much data in a frame, it depends on the word that it is. But because everything is a defined value, in terms of its size, what will typically happen is that it'll just interpret whatever the 20th bit in your frame is expected to be, as the parity bit, and so that will just decide whether it determines that the message is valid or not. What you can do is you can mismatch this data word count to the number of data words that you send. Because because you have this different sync, if the sync thing continues going on and the RT is not properly coded, you may be able to force data into there. But the fact that it is a specific size timing based thing along voltage, Manchester encoding stuff, can't really send like 17 bits of data in like a data word instead of like 20 or whatever. You could try shortening it sometime. I haven't seen that be like super successful, but you could theoretically shorten the data, shorten the word, and that might cause a problem for the RT where like you send a short word, then when data comes across next, is interpret data as the rest of the word. more than likely, because the timing gap would be too long, say that the message was valid. But if their message validation correctly, then you have opportunities there. Same with the data word count. You can try sending extra.
Did he cut out for anybody else? I give him 1 second. His internet goes down sometimes. I think they're doing construction right outside of his house. I'll send him a message. Oh, look, it's just me. He'll be back in just a second. You can look at my beautiful face until then. Just so you guys know, I have terrible stage fright. So if I pass out, don't be alarmed. Is there any other questions? You'll clip it. Thank you. Any other questions? No questions? I might know something. Probably not as much as he does, though. I did. I did hack some locks at Hackspace. I got the training lock just fine, and then everything else I could not do because I'm not great at it yet. It was my first time, to be fair. All right, let's see what his message says.
I am back. I apologize, guys. I'm in St. Louis, and we have kind of severe thunderstorms in the area, and are still recovering from the tornado last week. So my internet has not been the most stable. Okay, so back to where I was. So we talked about that. So those are the security concerns. This gets into what happens during unexpected transmissions. So if an RT attempts to transmit an uncommanded status word to the bus controller, by protocol, the bus should log the message as a violation and ignore it. However, this is where things are a little interesting in terms of standards and real life. It is relatively common for developers and manufacturers to have exceptions to when the remote terminals are allowed to broadcast on their own. Typically, this is in systems that either have like a startup status that's being sent to the bus controller. As they're starting up, they'll continuously send a command to the bus controller saying like not ready, not ready, not ready, and then ready, so that the bus controller knows when everything's going. You'll also see it sometimes if an RT is expecting to get data from another RT, which can be commanded by the bus controller to send data between the two. Then if it hasn't gotten it in a while, it can sometimes also be allowed to send a command to the bus or status word to the bus saying, hey, I haven't gotten any information, like do something about it. which means that there's opportunity for misconfigurations in the bus controller for us to attack, where we may be able to just send commands to the bus controller that aren't expected and do something with them. That's particularly like high target, like that's what we really want, because generally the bus controller is the flight computer. So if you can get control or command the bus controller, you can basically take over the whole aircraft from that point. So it is very interesting. In conjunction with that, though, like another interesting thing is, so flight computers have to go through like very, very stringent testing requirements for their reliability. A lot of times it's called DAL-A, DALA. I forget what the DAL stands for. That is like that's the highest reliability and safety requirement. Those they require all kinds of isolations for like your threads and processes and all those kinds of things. But that testing is so stringent that generally, if something is DAL-A certified, it is considered a secure device by the NSA. So it's just interesting how that safety and reliability aspect, all of the things they do to protect the functions and deterministic nature of the flight computer, actually result in fairly secure, or in pretty secure implementations as well, because everything is isolated from each other. You can't mess with memory regions in various ways because it's not allowed, because they have to prove that you can't do that, all that kind of stuff. So if an RT sends a message to another RT, though, there's no way to identify that it didn't come from the bus controller. Now, the bus controller may see a message that it did not send come out, but it may also just ignore it. And a lot of times what will happen is it won't treat that as nefarious. It'll just treat it as a violation, which means it will log that there was a anomaly on the bus at time X, and that's all it'll do about it. There's generally no active response on a aircraft bus. Partially for that safety reason, partially because people haven't had enough time to do it, or to figure out a good implementation to it, and partly because it's just a hard solution to, with the lack of like sourcing and integrity and those kinds of things on the bus, or non-repudiation, not integrity. So there are people working on stuff. There's some cool like people have built like firewalls for 1553, and they're pretty cool and they work fairly well. But again, you get into the safety issue, and none of them have been certified for flight yet, so it's pretty interesting. But we're gonna go ahead and jump over to our back to our little demo thing so that we can show what some of these look like. So we've been running for a while. So I'm gonna go ahead and stop the bus so that we can just send our bus controller from doing like its auto thing, so that we can see some stuff. So the first thing that I'm gonna do is let's try and send a command like as RT1 with a like, so this is where kind of like some of our stuff doesn't work as well. We'll send like an RT4 command with it addressed to RT1. What we should get is that it doesn't know what to do with the command, because when this gets converted with this RT4 part, the address will be right, but like the command word won't be right, or not the command word, the command mode or subaddress won't be right. So what we'll get it is, oh, RT4 didn't respond. It just said nothing. Yep, so it'll do nothing. That's interesting. That should have responded with an unknown command. There might be, like I said, this is still in beta, so there might be a few bugs in here. I do know if you type in RT1, like actually address it to it and then give it like a test command, it will, like when we spoof that message, you'll get an unknown command. So that's it behaving as it's supposed to. Basically, it's saying, I don't know what you told me to do. I don't have a definition for this command in my memory, And so instead of doing something with it, it tells you unknown command. Um, we can go ahead and try, um, spoofing, just asking like RT1 for to request a position. And when we do that, we'll see that RT1 gave us a position. So that's it responding to the bus. This bus or this implementation is written so you can actually send a unexpected command to the bus controller. Because I've seen it happen. So we're gonna move this dial down here. So we're just gonna scroll up and grab like one of the positions from a while ago, so it moves a bunch. So we have this. When we spoof it, there's going to be two interesting things that'll happen with it. So if you look on like through our logs, you'll see where is it? That the command that the bus controller sends to RT1 is to request the position. So we're gonna spoof a message onto the bus as RT1, like responding to the bus controller. Oh shoot, that was not what I meant to do. Responding to the bus controller with that position, and what you'll see is that we should get two things happen.
Hey, Jake.
Yeah.
Does the command words and data words get transmitted in hexadecimal LVDS question mark?
No. Well, on the in the simulator or on in the actual 1553.
Let me respond to him.
Okay.
And in the actual 1553.
No, so it's using that Manchester encoding. Everything is sent in binary. So theoretically, you can translate that to whatever you want because you can send hexadecimal in binary. Sometimes some devices do that; they'll send the values in hexadecimal, but it's just converted to binary. But everything on the actual bus is binary.
And he asked how it handles race conditions.
Yeah, so race conditions are so the protocol has no way of validating race conditions. If you transmit especially if you're talking about influencing the bus controller, if you manage to inject a message in the gap between when the bus controller sent a command and when the expected RT responds, you can totally hijack that response because the bus controller is expecting a response. And generally, the gaps are enforced as a no larger than, not a no smaller than gap. So if you can find a timing gap to inject into and race the terminal, the bus has or the protocol has no way of dealing with that. How race conditions within the RT or the bus controller occur, that's dependent on the device that you're targeting. We'll talk about it in a second, but when we start getting into like trying to break like the commands that are going to the RTs rather than abusing the protocol directly, um, other than sending it in 1553 protocol speak, the stuff you do for like fuzzing an RT to try and find like buffer overflows and that kind of stuff is generally the same concepts as a like testing an API. So you get so we'll look at what an ICD looks like. You'll get all the values in it, and then you start identifying things like it's really common for like developers to build like they'll say in the ICD that the command is supposed to be like a oh man don't make me do this d long and then they end up implementing an integer because they intend to extend the command at some point to take in more data like in a future thing, but then someone writes the code as like just the size of the current, and when you do that, you then potentially have buffer overflow issues depending on how those data words are handled when you send it, because it'll say that the data word or that a spot in the data word is supposed to be 4 bits. They're really only using 2, and then what is being done with the second 2 bits is up for debate with how the RT actually handles it. So that's kind of how you'd go about attacking like RTs directly, rather than attacking 53 protocol.
HX47 says he's working with aviation in the aviation sector. It's frustrating dealing with cybersecurity companies that don't understand aviation, trying to sell us OT solutions designed for oil and gas, which aren't compatible with aviation protocols.
Yeah, I totally feel your frustration on that one, because I had that issue a bunch when I was still at Boeing. I was like a hiring manager and like a purchaser for Boeing when I was there. And every tech conference I went to, all those vendors tried to convince me that their OT solutions were adequate for what we were trying to do for aviation, and they just had like no idea that like it didn't work at all for what they were doing. So I totally feel your pain there. It is very frustrating because it's a very niche thing. One of the interesting things, and sorry, I'm getting sidetracked here, but I just like this is like one of my soapbox things. When you're talking about some of these niche areas, like that are really operations focused, like aviation, even some in manufacturing and stuff, finding people that understand the industry is sometimes more important than finding people that understand the actual technology. Like we used to, when I used to hire, like it was much easier to take someone that was like an aviation technician, like a avionics technician from the Air Force, or like had worked at like Delta doing mechanics or something, and teach them the security principles than it was to try and teach like a security guy the aviation principles, because they just didn't really understand the influences that like um, all of the checks on operations, all of the reliability requirements, and all that kind of stuff. So yeah, just kind of interesting there. Um, but okay, so now that I'm off my soapbox, we'll go ahead and I'll show what was gonna happen. So you'll see this. So I don't know if you saw that, but this jumped from leaning to the right to now leaning to the left. What's interesting is that RT1 will give a um, will give an unknown command, and that's because when we go back to here, when we go look at these again, um, the sync command for the status word and for the command word are the same validation. And as a result, when we respond with what RT1 which should have responded to, and RT1 hadn't received a command word yet, it interpreted it because of that remote address as a command. And so if you were to start trying to build like detection algorithms and stuff for a bus, that's like some of the things that you can start looking for, is like if someone's trying to spoof a command to the bus controller, RT1 is going to respond as if it didn't know what was going on, because it thinks that it was sent a command. And so there's some interesting behaviors there that pop up if you're collecting logs that you can look at for things on avionics. But 9 times out of 10, that's not going to cause any problem on your bus, because the RT is just going to assume that it was a corrupted command that it didn't know. So it'll send a status word saying like, "Hey, that didn't make sense to me." The bus controller will have already gotten its response that it's expecting. So it just sees that, and then it'll go, "Oh, weird, RT1 like double like sent me 2 commands. I wonder what happened." Like it may say, like ask for a status update after that, like because it saw like an error message come from it, say like, "Are you good?" But for the most part, it's gonna get, after that, everything's just gonna work as normal, and so like they'll just kind of forget that happened and keep going on. Um, so like that's just kind of an interesting thing to do there. Um, so we'll go back to here and back to our slides. So we only have like 2 more slides, and then I'll talk about a few more things. So interface control documents. Oh wait, I guess swap this. So interface control documents are what tell you what is supposed to be in each of those windows and those data words and stuff. They're super dense documents. that have like a TR that have like will tell you whether or not the command for this one. This is just like what the command words for an RT will look like, and by like are the defaults for the protocol. I took this out of that AIM document because it has just like command words are by protocol. But this is what it'll look like. It'll have all these information about like whether it's supposed to be a transmission or a receive, what the mode code is, then like the definition of what that mode code means for your function, and then also like if there's data words, how many data words, and all that kind of stuff. They're really dense documents because they're literally just like documents with bits and binary, bit flags and binary in them with like individual things that'll tell you values. Uh, I actually built at one point at Boeing a entire parser in Excel where you cut and paste like because that was the only thing that the other people in my office knew how to program in was VBA. So you could cut and paste in Boeing's ICD documents and pull all the data words out and like build a fuzzing protocol for you off of the stuff. It was pretty cool. Um, but super dense. So these ICD documents are not generally public knowledge. That's why I had to use a generic one. I couldn't find any open source um, ICDs to show you guys. But yeah, so they're super dense, but they have really important information in them. This is where you'll see things like they tell you that it's only 4 bits. Like when you're looking at the data words, you'll see like data words, and they'll define it. They'll say the data word is 16 bits, and that a field is supposed to have 4 bits. And then you look at it that it says it only accepts values like 0, 1, and 2 as integers, but they have like a full integer byte there or a full like d-long byte there, and you're like, okay, what are they doing with those other bits? And so you can start attacking. That's how you can start designing like fuzzing protocols against like RTs. Um, Unfortunately, we don't really have a good way of doing that in our simulator currently. It does have the ability to send it an invalid command that you guys can kind of poke around on. Um, so Um, so we have it in here. If you set RT1 and then you do set position. So generally we're talking to the INS, which stands for Initial Navigation System. As part of startup, you'll generally have a way, a like alignment function, like an alignment uh, protocol or methodology that it does for aligning the aircraft so that it can determine what that looks like. So a lot of times it has to be fed an initialization vector. So this like set position, and then this is just kind of a dummy one. Like it doesn't really matter what value you put in. If you spoof this, you'll see it returns like all zeros because it crashed, and then you'll see a second, yeah, that it restarts. So there's so like that's kind of what typical behavior would be if you do manage to crash an RT. A lot of them are configured to auto reboot when they have they'll have like fail safes where they have like a voltage indicator on part of the RT. It's like a separate kind of module, and if there's that voltage is on, then the RT knows it's supposed to be on and it'll reboot. And so it's kind of interesting to play around with those. I encourage you guys to poke around on some other stuff. I didn't display what the. We'll go ahead and start the bus controller and display what our toggle DOS thing does. So we're getting all our stuff. If we toggle this on, you'll see this. Yeah, and now all of a sudden the bus is inaccessible and we're just getting constant collisions. So like nothing's working anymore. So you'll see all of this has stopped updating. It says the bus is open even though the bus is inaccessible. And this is kind of what you'd actually see happen a lot of times, depending on how you're doing, like determining if the bus is available. This may just permanently stay closed depending on how things are going. But we'll turn this off. So and then it starts going again once the DOS attack has stopped. You can pause your logs, and so like a fun one to play around here, like we can spoof our RT4 stuff. For RT4, you can set the engine temperature to like 1,000 Celsius. Oh, apparently that is out of bounds, and that crashes. So don't set it to 1,000 Celsius.
Jake, you good for a few questions?
Yeah, I'm great for a few questions.
First,
Oh.
Baked Beans wants to know: could you use ML to analyze traffic data, common things like conditions, rather than use ICDs?
Yes, you can. There are a few people that have started trying to. Oh, I know what's happening. I'm trying to inject into the bus when it's not available. That's why it's not working. There we go. So you'll see again, like it got an unknown command, but then now we've made our engine tempt. Yes, so you could. There have been a few companies. Peraton, I believe, was one company that was working on that, like a bus monitor that you hooked up to the um to the to the aircraft, and then let it collect data for a specified amount of time, and then they would process the messages, and based on like behavior and stuff of the aircraft, they claimed that they could back out like ICDs from that, to determine like what the aircraft was doing. So that is definitely like an interesting area of study. Um, there, when I last saw it was like a year or two ago, and it was still very much like a beta product, but it was definitely intriguing. Like it worked well enough that um, like I would like to see where they go with it in a few years. But yeah, you can totally use ML to baseline a bus architecture, and then start trying to assign meanings to those values and try and fuzz it that way.
And could you ask Jake how he interfaces with the bus, or does he just use AIM products?
So for interfacing with the bus, it depends. I really like AIT products is what I really like to use. They're a little pricey. Um, I believe that's the AIT, Avionics Interfaces Technologies. Their stuff's really expensive, but it is like really good. And then what is the other one? It's been a while since I had to buy it myself. There's another one that's
He says we know it's expensive.
yeah. I really want to get like some more stuff to build out a lab for everyone, but man, Alta DT is the other one that I like. But yeah, they're just not flexible on their pricing, because I wanted to build like a range with because AIT has a really cool bus emulator that you can buy and actually like, connect to a 1553 bus, and it'll emulate like a bunch of RTs and stuff for you. But they're very proud of that device. So, and then someone asked, does the C1553 not help mitigate? Oh yes. So the entire point of the dual thing is to mitigate like a collision on the bus. Like so, under normal operations, if a RT was misbehaving because of a short or because of like bad logic, and all of a sudden it was just spamming the bus, the bus controller would fail back to the redundant bus and then command the other RTs to start operating there. But it so it mitigates it from like accidental stuff. And then it depends on how the RT was designed. So it may have internal controls that would keep it from sending data to both buses simultaneously. But if you're talking a malicious attack, there is like nothing that actually um, prohibits the RT from talking on both buses simultaneously, unless it has internal controls to prevent that, or is just built in a way that you can't do it. So yes and no. Um, there's been talk of introducing hardware diversity. So typically on aircraft, like we've been talking about, like the flight computers, typically flight computers are at least triple redundant. usually triple redundant. They don't usually go more than that, but occasionally you'll see like a quad redundancy or something. Are triple redundant. But the problem is that they are generally the exact same hardware with the exact same software. So if an attacker had figured out a vulnerability against the flight computer stack, the triple redundancy would be unlikely to help. Triple redundancy really just helps the aircraft from hardware failure in current implementations. So that's kind of the challenge there. Um, you can, so in certain redundancy things will help. So like the famous one, like with like pitot tubes and the angle of attack indicators from the MCAS stuff at Boeing. If you have three angle of attack sensors, spoofing all three devices or all three RTs at once is like a much harder challenge, especially if you only have one device on the bus that you've compromised. So it does help a little bit there because the data sources um, are a little more resilient because you may spoof one, but then the other two might have correct data. It's not impossible to get around, but it makes it harder. And then I forgot the other thing that I was gonna say. Nope, totally lost my train of thought. Sorry. Any other questions, Andrew?
I don't see any. I see coaches in Discord general chat just talking about the products that they're trying to use.
Um, oh, so someone asked, Baked Beans asked, in my experience with testing, to the lower assurance DAO LRUs. A little bit. You definitely get less robustness in the code reviews, and so you do tend to find a few more errors, but like uh, generally quality assurance on these devices is pretty high. Or well, okay, they're really good at testing devices in the aviation industry for behaving how they're supposed to behave. So they're really good at checking that does the device, when you send it a like nonsense, like just a garbled message, does it recognize the message is invalid and discard it? They test for that kind of stuff. They're really good at it, even at lower level DAOs. They're really good at testing, out of sequence stuff like the protocol non-compliance stuff tends to be fairly robust. Occasionally, you find stuff that is fine with it because they wrote it in a way that they didn't really think about the repercussions. They're not good at testing for intentionally malicious stuff. So, like, if you start flipping like the aircraft's like positioning, like on our navigation window, if you start flipping it from upright to upside down, some of the lower DAO stuff will not have anything built in to address the data variance there. So then you can start causing issues. Same with some of the radios for RF stuff. There can be problems in how they handle certain protocol stuff. Without saying too much there. So the lower assurance stuff does tend to have more issues. I mean, and when I say more issues, most of the stuff still we didn't find a lot most of the time. It's more when you start trying to do spoofing and deceiving the devices in a correct but malicious way that the aviation devices have a much time. So hopefully that answered your question. But yeah, there's a lot of assumptions that the data source is always going to be good in the systems, which has other complications. So like we spent a lot of time evaluating how flight computers, especially when you're talking fighter aircraft, where the aircraft is inherently unstable. So like if the flight computer goes out, the pilot has no chance of being able to control the aircraft because it's inherently unstable. It'll just start tumbling. Um, More often than not, like letting the malicious code run and attempting to recover either through pilot actions or like a reboot or whatever you're trying to do is better than just like, you know, like the angle of attack sensor is acting in a malicious way, so we're going to cut off the data. No data is almost always worse than malicious data in a aviation context, which is like a very unique kind of concern for the aircraft because if they're getting bad data from a data source, the flight control algorithms have a chance at recovering the aircraft because they eventually realize that the data is no good and go into something else. The pilot may be able um, to recover like physical controls. Like there's a couple options, and so it's almost always continue the malicious data being sent across the bus than it is to just cut it off, unless it's like a like in a commercial aircraft, like the flight entertainment systems are being malicious, then obviously you just cut them off because it's not a mission critical or flight critical system. But if a flight critical system starts misbehaving, generally you reboot and try and recover it into the usable state, or you just continue let it doing things unless it's like a full on like denial of service bus, like it's just locking out the bus.
Somebody wants to know the name of the software.
Which software?
It was about a minute ago, so I'm trying to juggle all these questions. Ask. While he responds, does Jake recommend fighting off but you need physical access, and we have armed guards argument for achieving proof of concept on attacks?
So yes and no. I think especially in operations forward contexts like aviation, that sometimes we have issues in the security industry of not accounting for that. Like I have seen the security reports of like when I was in the military of like a pen test team came in and like wrote there were a million like catastrophic failures in the system. And then when someone asked like, well, how did you get access to the system to show that it had a weak password or whatever? And they're like, oh, well, we white carded past the armed guards, the locked door, the safe that the device was in, and then we got access to it, but it had a weak password, right? Like, so I've definitely seen that happen. And when that kind of thing happens, there is validity to the argument that, like, hey, you just like waved past like 6 layers of security. You can't just like totally ignore that. Now, there's a lot of times where people insist that because they have armed guards and stuff that things aren't real, or you can't reach the aircraft. That gets into that air gapped part of it, where they're like, well, we're air gapped and there's all this security, so you can't reach the aircraft, so you can't do anything. And they don't account for the fact that like map data comes from like publicly accessible like internet sites. So if someone was to able to compromise like where the map data for the navigation system is being pulled from, then they have a way to get on the aircraft because that data is inherently just transferred to the aircraft when you start doing your mission planning. Um, Same with some of the wireless protocols where they don't really think that it's possible to do anything with them, but there's enough open source use cases of people like that DHS thing and stuff where people have at least acknowledged the existence of that happening. That's not really a valid argument, in my opinion, anymore. So I think a lot of it is context matters, which is like always the like unfun answer. But that's kind of the true one. I do think that there is some validity to the argument of like, um, what's it, guards, gates, and dogs or whatever type of thing. But it is context driven, and a lot of it is also supply chain. So that's the better argument is there's been a high incidence of counterfeit parts in the aviation industry over the last 10 years, like very high uh, incident of counterfeit parts. and so supply chain access is not a unrealistic scenario either.
I don't see any other questions.
Okay, cool. Well, I will do one marketing plug. If you guys liked this, we are teaching a whole 4-day course on aviation and ICS SCADA security stuff at Black Hat this year. The prices go up on the class at the end of the week, so I'd highly, if you're interested, please go sign up. I apologize for anyone that was on the Zoom. I'm unsure of what caused that because I haven't used the account that the Zoom meeting was under, hadn't been used in like a year, and our Zoom scheduling had been like disabled for on our other account for like 8 months now. So I'm not sure how that happened, but I really apologize for that. I know that was probably frustrating, so I apologize.
You may link the aviation class and
Yeah.
right. It's the ICS security boot camp, right, Jake?
Yeah.
Right.
It should say Aviation ICS Security
Yeah, I
Bootcamp.
got it. I got it.
Yeah.
Go ahead and link that in all of the places.
Yeah. And if we, as we make updates to the simulator thing, we will definitely like push those to the repo, and I will try and. Vincent is much better at Docker than I am. I thought I had a handle on it, but I will make the install process cleaner for that, where you can kind of just, you should be able to just pull down like one YAML file instead. So we'll get that cleaned up.
Hold on, you get one last question, I think. Could you talk a bit about what you're planning for the firmware analysis part of the course?
So Anthony is like our firmware reverse engineering expert on that. So unfortunately he's not here, but generally it'll be using things like he's like a big fan of like Binary Ninja to look at it, to look for various places that you can decompile code. We do that most often on ICS type of systems. Like we just did it for some solar power stuff, and we submitted for like some solar CVEs, which hopefully will be coming public shortly. They so it'll be looking for things like management functions that may not require authentication, identification um, of maybe undocumented functions, looking for hard-coded credentials, because that happens a lot in ICS systems where there's actually hard-coded credentials within the firmware. And then kind of things along those lines, if that helps answer the question.
And Baked Beans, I'm going to link it again. There's our Discord. If you ever have any questions, feel free to join it, and you can always ask anything. We're always usually around.
Yeah. Yeah, if no one else has any other questions, I'll stick around for a few more minutes. Feel free, but that's kind of what we had for today. Thanks for joining us. Appreciate it. Cool. Well, Andrew, did you have any questions for me?
Besides 1553, hold on. I wrote them down and then I forgot them immediately. Hold on. I did have questions though. Let me scroll back up. Besides the low data rate, and I guess it's aging technology at this point, and the limited skill, like you can only have 31 remote terminals. Like, what are the other disadvantages
Mhm.
of 1553? That was the only ones I caught though. There might be something I missed.
Okay. So 1 second. Yes, I will put up the slides. I will be in that 1553 simulator project. So we'll put them in there. So 15 the primarily disadvantages just from a like performance standpoint are the throughput and the weight. 1553 compared to like fiber optic and stuff is much
Yeah.
heavier. And you have less relevant on like a fighter, but on like the big on the like big commercial craft, you also have run length limitations on how long the cabling can be before you have drop off in reliability and performance of the protocol because using that twisted copper line. So fiber optic protocols using like A-Ring 664 or the like TCP/IP version of 53 have like significant more performance there. But yeah, weight is the biggest issue for aircraft,
Okay.
especially when you're talking like fighter performance aircraft. Like the like weight is like their biggest issue on trying to um, build things. Like they're measuring every ounce when they're designing those aircraft.
So it came out like 1970, so it makes sense why like cybersecurity was never really in, and like they weren't really thinking about it back then.
Mhm. Yeah. Well, cool.
Pretty much
We'll
the only
call it a
questions I
day.
got.
Okay. Yeah, we'll call it a day. And thanks everyone for coming. Feel free to join us on the Discord. And let us know what you think. And again, like I said, I apologize for the issues with the Zoom link today.
Awesome.